We tend to think of a computer bit as a physical object, a microscopic switch flipping on and off inside a silicon chip. Early data storage was mechanical. You either punched a hole in a paper card or you didn't. The machine read the physical presence or absence of matter. That physical movement eventually became electrical logic. Huge banks of wired relays clacked back and forth to route currents through a system. Then came vacuum tubes, which removed the moving parts. But they still required massive, fragile racks of glass and metal to hold an electronic charge. In 1948, the definition of the bit shifted. It was characterized as a measure of information entropy, existing independently of the machinery used to store it. Moving past the hardware to see the bit as a mathematical law makes it possible to calculate the absolute theoretical limits of computation. In 1947, a statistician named John W. Tukey was working at Bell Labs. He was focused on the sequential conversion of continuous analog data into discrete digital steps. Engineers working in a base-2 binary system lacked the vocabulary to describe the place values they were calculating. They had digit for the base 10 decimal system, but nothing for binary. Tukey solved this by contracting binary digit into a single word, bit. He specifically defined the bit as a generic name for a coefficient in a binary expansion. His terminology outlasted other clunkier proposals of the era, such as binit or bigot. Tukey's model converted analog measurements by sequentially dividing the data into halves, quarters, and eighths. Each division generated a 1 or a 0, turning a continuous line into a digital string. This linguistic invention gave mathematicians the conceptual vocabulary they needed to formalize digital architecture. The following year, Claude Shannon published his landmark paper, A Mathematical Theory of Communication. Shannon established that to measure data, the actual semantic meaning of a message must be ignored. Instead, information capacity relies strictly on quantifying the total number of possible states in a system. This chart shows the linear growth of information capacity. The number of possible states doubles exponentially, making a base 2 logarithmic scale the natural choice. Adding one relay doubles the possible states, but adds exactly 1 unit to the base 2 logarithm. Shannon used this logic to define his entropy formula, a measure of the uncertainty generated by an information source. The variable pi represents the statistical probability of a specific symbol occurring in a message. In English, for example, the letter E has a very high statistical frequency, while the letter Q is rare. Knowing these probabilities allows for data compression, where the shortest binary strings are assigned to the most frequent symbols. But transmission is rarely perfect. Physical interference creates a noisy channel that disrupts the data. In this environment, bits are randomly flipped from 0 to 1 or 1 to 0. Shannon defined the mathematical measure of this missing information as equivocation. By using the bit, he calculated the exact amount of redundancy required to achieve perfect error correction. Shannon's isolation of the bit as a mathematical unit of entropy proved any data could be perfectly compressed and transmitted, birthing information theory. In June 1948, as Shannon's paper was going to print, his abstract theory was being realized in physical hardware. The Manchester Baby ran the world's first stored computer program using electronic memory. It utilized the Williams tube, the first high-speed RAM, to physically store those newly defined theoretical bits as charges on a cathode ray screen. While the bits themselves were mathematically elegant, the facilities required to process them in the 1950s remained massive and industrial. The hardware would soon shrink, but the core revolution was the realization that all future computation would be governed by Shannon's mathematical laws. As computers became more powerful, engineers began grouping individual bits into fixed sizes for more efficient memory addressing. In 1956, IBM engineer Werner Buchholz coined the term for these groupings, the byte. He chose to spell it with a Y specifically to prevent engineering manuals from confusing the word with bit. The industry eventually converged on a standard grouping of 8 bits per byte. Mathematically, an 8-bit byte allows for 256 distinct combinatorial permutations. Those 256 values provided enough capacity to map every standard letter, number, and symbol in early encoding systems. Today, these groupings scale up into the metrics we use for every file we own: kilobytes, megabytes, and gigabytes. These massive byte arrays are what allow us to render complex audio waveforms and the full color spectrum of modern displays. Every modern architecture, from smartphones to 64-bit processors, still functions using this same fundamental base 2 math. The modern digital universe is essentially a scaled-up application of Shannon's entropy equation and Tukey's terminology, confirming that the bit remains the base unit of all information.